Hello everyone. My name is Suvrat Mehta, and today we'll be discussing CodeChef Starters 2 and 4. Is the recording on? Yes. Okay, so let's start with the discussion. The first problem, zero permutation score. Chef has an array A of length n, initially A1 equal to A2 till AN is equal to 0. Chef wants to transform this array into a permutation of the integers 1, 2 till n. Chef may perform the following operation any number of times. Select an index I such that 1 is less than equal to I and is less than equal to n. Update the value AI to AI plus 1. After every operation, compute z as follows. Z is the number of indices j such that 1 less than equal to j less than n and both adjacent positions are 0. Aj equal to 0 and aj plus 1 equal to 0. Chef's score is the sum of z overall operations performed. Your task is to determine the minimum possible score chef can achieve while converting the array into a permutation of 1, 2 till n. And the constraints are t is less than equal to 100 and n is also less than equal to 100. So expected time complexity would be till O of n square. So basically we have an array A which is initially all zeros, and we can perform operations. In one operation we can set the value of AI to AI plus 1, and Z is the number of indices I such that AI equal to 0 and AI plus 1 equal to 0. And basically what we need to do is we need to take the array A and we need to perform the operations, and we need to transform this into a permutation. And sum of z value after each operation. Actually, minimum sum. So let's see the test cases. So these two test cases are not good. Let's see this test case 4. So 1, 2, 3, and 4. So the first operation we can either make this one, or we can make this one, or we can make this one, or we can make this one. So if we make this one, then we would have a z score of 2, and if we make this one, then we will only have a z score of 1. So similarly, if we make this one, we will have a z score of 1. If we make this one, we will have a z score of 2. So it's better to make this one, right? Because that would make our z score equal to 1. And this and this indices can never be, this and this indice can never now contribute to a z score. So after the first operation, this will become 0, 1, 0, 0, and z is equal to 1 here. So now we can see that this index and this index can never become a candidate for z value, z score. So again, what we can do is we can skip this 0 and we can mark this as 1, so that now these two indexes become not, so that these two indexes can now not contribute to the z score. So basically after the second operation, the array will look like this, and we can cancel out all the indices, the possibility of all indices being contribution to the z score. So z is equal to 0. So overall z would be 1. Sorry, answer would be 1. Let's see the next test case 8. So 0, 0, 0, 0, 0, 0, 0, 0. So obviously again we'll follow our same strategy, since we want a minimum number of indices that are possible that are contributing to z value. So we will make this as 1 first in the first operation. Then in the next operation, we will make this as 1, because after making this as 1, we are ensured that these two indices can never contribute to z value. And next, when we make this as 1, we are ensuring that these two are not contributing to z value. So basically in each operation, we are reducing the number of z score, we are reducing z score by 2 basically, since we are removing two indices. And that is the maximum number of indices you can remove in a move, because no matter where you place one, you will be only able to restrict two indices. So 0 1 0 1 0 1 0 0, and then in the end we will get this. So here the score is 2 1 2 3 4 5, then it will become 3, then it will become 2, then it will then it will become 1, then it will become 0. So 8 and 9, 9. And once we have this array, what we can do now, we are simply allowed to perform any operation, since the z score has become 0 only, right? And z score will not go below 0. So what we can do is we can just perform any operation. We can make this 9, we can make this 8, sorry, we can make this 8 7 6 5 4 3 2 1. It does not matter, we can perform any operations, the z score will always remain 0 only. So basically the answer for this was 9. So basically we are solving this question on based upon two observations. The first observation is, in each step, actually operation, we can reduce the z score by a maximum value of 2. And the second observation is, once the z score reaches 0, then it will always be 0. So basically we are allowed to do any operation. So based on these two observations, we can say that just marking the alternate ones would be the optimal strategy here. So overall score answer would be something like this. Let's take the example for n equal to 8. So initially 1 2 3 4 5 6 7 8. Initially we had 1 2 3 4 5 6 7 1, sorry. So 1, 2, 3, 4, 5, 6, 7. So 7 indices there were initially, with a pair of where the values were 0 0, adjacent values were 0 0. So there are 7 indices initially. And after each operation, we reduce the z score by 2. So 7 becomes 5, that becomes 3, that becomes 1, that becomes 0. So the answer is 5 plus 3 plus 1 equal to 9. Similarly, for n equal to 4, the initial score would be 3, then it will become 1, then it will become 0. So 1 plus 0 is 1. The answer is 1. We don't need to add this 3, because we need to only add the z scores that we get after the operation. So we need to add from here. So basically the solution would look something like this. While n is greater than 0, simply add answer plus equal to n and n minus equal to 2. And once I see in n, I can just n minus equal to 3, so that I immediately come to this step. For 4 it will be 1, for 8 it will be 5. So you can do it like this. This would be O of n time complexity, and O of n pass pretty easily. So this is the solution. LLN, CNN, L answer is equal to 0, n minus equal to 3, and while n is greater than 0, so answer plus equal to n and n minus equal to 2. That is the solution for problem A. Let's move on to the problem B. So chef has two permutations A and B of length n. Here a permutation of length n is an array containing each integer from 1 to n exactly once. Chef wants to transform array A into array B using the following operations any number of times. Choose an index I and either increase AI by 1 or decrease AI by 1. However, after every operation, including the initial and the final array, the following condition must always hold: AI not equal to AI plus 1. Intermediate values may become any integers, they do not have to remain in 1 to n, and A does not have to remain a permutation, but the final array must be exactly equal to B. Determine whether it is possible to transform A into B while maintaining the adjacency constraint at all times. Print yes if it is possible, otherwise print no. And the constraints are n is given less than equal to 2if and the sum of n over all test cases does not exceed 2if. And obviously all AI and all BI are different since they are permutations. So, okay. Problem B. So in this problem, basically we are given two permutations, A and B, and we need to transform the permutation A into permutation B, where the operations that we can do are AI, we can make AI plus 1, or we can make AI minus 1. Basically, we can increase or decrease the value at any index. So, and also while we need to maintain the condition that AI is never equal to AI plus 1. And we need to answer if this is possible, yes or no. And the expected time complexity would be O of n log n. So let's see the test cases now. So the first test case is 1 to 1 2. Since A is already equal to B, so we don't really need to check anything. The answer is obviously true. And the next is 1 to 2 1. So 1 2 2 1. So we need to transform 1 into 2 and 2 into 1. So basically, no matter what we try, we will have to increase 1 at some point, and the moment we increase 1, it will become equal to 2. So basically, it's not possible to make this one into 2 without ever making the adjacent values equal. Since we can look it at we can look at this in a way. Basically, AI, this is, let's say this is AI and this is AI plus 1, and this is BI and this is BI plus 1. So basically AI, let's try to draw a number line. So here is a number line, and here we have AI, and here we have AI plus 1, and we have BI plus 1 over here and BI over here. So basically, according to the given operations, what we can do is we can either move AI this way or AI this way, and similarly we can either move this here or this here. So basically, since the end position of this is here and the end position of this is here, so we can see that no matter what direction we move them in, at some point they would have to collide with each other. Only then they would cross the paths, because initially AI and AI plus 1 are like this, and then finally AI plus 1 and AI should look like this, right? So they are crossing their paths at some point. That must be true. That has to be true. So basically, we can say that observation that If AI and AI plus 1 have to cross their paths to reach BI and BI plus 1, then false, because obviously then at some point AI will become equal to AI plus 1, so not true. Let's take some example to understand this better. So let's take an array. Let's say there is some permutation where AI is equal to 3 and AI plus 1 is equal to 8, and the final value is BI is equal to 6 and BI plus 1 is equal to, let's say, 4. So basically on the number line they would look like this: 3, then 4, then 6, and then 8. This is AI, and this is BI plus 1. This is BI, and this is AI plus 1. So we can see that this needs to come here and this needs to come here. So obviously they will cross their paths at some point. There is no way that they do this without crossing their paths. So yes, they would have to cross their paths. So in this case, basically the answer will become a no. Or else if we check some other cases, let's say the numbers were same, 3, 4, 6, 8. Let's say this was AI and this was BI, and this was AI plus 1 and this was BI plus 1. So now we can see that we don't need to cross our paths. With AI and AI plus 1 don't need to cross their paths. So basically the answer will be yes in this case. Similarly, if let's explore some more cases. Let's say this was AI and this was BI and this was AI plus 1 and this was BI plus 1. So this needs to go there and this needs to go there. So basically, although this might seem at a first thought, this might look like that AI and AI plus 1 are crossing their paths, but no, what we can do is basically we can move first AI plus 1 to BI plus 1 and then move AI to BI, so they will never actually cross paths. Since you can see, basically the thing is, at the beginning, AI is less than AI plus 1, and in the end also, AI is less than AI plus 1. So basically, their parity, you can say, remains the same. Their order remains the same. So they don't need to just keep going in one direction only, right? So they don't need to collide with each other. They don't need to cross paths. But if we see this case, AI is initially less than AI plus 1, but AI would become greater than AI plus 1 in the end. So basically, since they are reversing their order, at some point they must be equal to each other, only then they can reverse their order. So that's why this is no and that's why this is yes. So I think we can point this out that if the order is same initially and finally, then yes, else no. And how can we check if the order is same initially and finally? We can just look at this condition. If AI is less than AI plus 1 and BI is greater than BI plus 1, then this is a no. And similarly, if AI is greater than AI plus 1 and BI is less than BI plus 1. So this is no. So we just need to check for these two cases over all the I indexes I, and even if at one index I this condition was true, then the answer would be no, because AI would have to become equal to AI plus 1. So this would be an O of n solution. which is well within the time limit. So let's see the code now. So vector LL A and B, I take input the vectors and then I check for the order. If initially and finally orders are different, then I mark this check variable as false. And then in the end, if the check variable is false, then the answer is no, else the answer is yes. So that was the second problem. Let's move on to the third problem. So delete for fun. You are given a circular binary string S of length n, that is position 1 is adjacent to positions 2 and n. And in general, position 1 is adjacent to I minus 1 and I plus 1 with indices taken modulo n. You are also given a starting index k. You must delete all n characters from the string one at a time following these rules. Your score starts at 0. The first deletion must be the character at position k. After deleting a character at some position p, then the next deletion must be from one of the two characters currently adjacent to p in the remaining circular structure. Let the character deleted on the ith move be c. If I is odd, your score becomes plus c. If I is even, your score becomes minus c. After every deletion, including the last one, your score must remain strictly positive. Your task is to determine whether such a deletion sequence exists. If it exists, output one valid sequence of n deleted positions. If it does not exist, print minus 1 instead. And again, the constraints are similar. N is less than equal to 2e5 and the sum of n over all test cases does not exceed 2e5. I'm audible, right? Hello. Okay. So problem C. Basically, in this problem, we are given a binary string S, which is circular in nature. So circular binary string S we are given. And the operations are like this. We need to perform moves where we delete some character in the string. And basically, if ith move, if I is odd, then basically the score becomes plus C. If I is even, then the score becomes minus C, and C is the value of the element that we just deleted. So, and also we must start with deleting the index k, and basically when we delete the index k, the only next indexes that we can delete now are k minus 1 and k plus 1. And let's say the next index we delete is k plus 1. So now we have two options. Either we can delete k minus 1 or k plus 2. If we delete k minus 1 now, so we have two options, k minus 2 or k plus 2. So basically we can just delete the adjacent elements only. From the last element that we deleted, we can only delete the adjacent elements. So let's see the test cases. So the first test case is 2 1 1 1. So k is basically the index that we start from 1 1. So first move is odd. So basically we will add the plus c, and the second move we will subtract. So obviously yes, we have to start the deletion process from the kth uh, element. So since kth element is 1, so we will start by removing this element, and since the move is odd, our score will become 1, and now we have this array left. And then since we only have one single choice, so we would have to remove this element. And since the move is second, so it is even, so minus c. So score will become 0. Since the score had become 0, the answer is minus 1. Since score must remain strictly positive. Then the next test case is 2101. 2101, yep. So k is equal to 1 again and then 0 1. So we will have to take this 0. So our score remains 0. And here itself we lose the game since the score must be strictly positive at all times. The next is 2201. So k is 201. So we will have to take this one and then we will have to take this 0. So our score first becomes +1, then we have this 0, then our score remains at 1 only. So the answer for this is first we remove this index, then we remove this index, so 2, 1. Then the next test case is 4, 4, 1, 0, 0, 1. So 4, 4, 1, 0, 0, 1. Um, k is equal to 4. So we start by deleting this index. So our score will become 1, and the only next index that we can delete is this. So 1, 0, 0, and we can only delete this since we can, oh, also we can delete this. Since the array is circular, these two are adjacent to each other, right? And since the first element that I deleted was this, so now I can choose from the elements that are adjacent to it. So now since this is the second move, then we will be subtracting from our score, right? So obviously if we subtract 1, then our score will become 0. So we can just subtract this 0. So the array will look like this, and since we are removing this 0, we can now next remove this 0 as well because this is adjacent to this 0. So we have two choices and our score remains 1. And then basically in this move, since this is the third move and we will be adding to our score, so we can just remove this element and then we will finally remove 0 and our score obviously will never go below 0. So the order in which we are removing the elements are first the 4, then 3, and then 1, then 2. Okay. And the last test case, 4, 2, 1, 1, 1, 0. So 1, 1, 1, 0, k is equal to 2. So k is equal to 2, we will remove this element. So our score becomes 1. And since we removed this element, we only have two choices now. And whatever choice we make here, our score will decrease by 1 and it will become 0. So that means the answer for this is -1. So basically, let's just first take the obvious. What is the obvious? That we have two choices to choose from at every step, right? So we have two choices to choose from at every step, right? Obviously, because we will be just taking whatever element we choose, the element that is adjacent to it will become the new choice. So we will have two choices to choose from at every step. Now let's analyze. Let's mark one of the choices with the variable L and one of the choices with the variable R. So let's say that what could be the different cases? Either they can both be 0, or they can both be 1, or they can be 1, 2, or they can be 2, 1. Sorry, 1, 0 and 0, 1. So what happens if both are 0? Then obviously our score remains same no matter what. Let's say that we also have two different cases when it is the odd number move and when it is the even number move. So let's say that up until now our score was positive and now we have to make a choice from these, and our I is odd or our I is even is given by this. So basically if the both are 0, then we can choose any one of them and still our score will remain positive. So it is fine here. Then if both are 1, then basically we will have to subtract 1 from our score no matter what choice we make, and that might make our score negative. So -1 we will have to do. Oh, when it is odd, then +1, and when it is even, then -1. If it is 1 or 0, then obviously when it is odd, we can select the 1, so our score increase by 1. When it is even, we can just select this 0, so our score remains the same. So basically in both the cases, we can manage to let our score remain positive. And here also we can apply same strategy. When odd, we can take this one. When even, we can take this 0. So again, our score can remain positive. And here also our score will remain positive. So the only problematic thing is this. The problematic thing is this. So basically, one more thing. Let's analyze this case a little more. So L, R, both are 1, 1, and I is even, right? So we will have to do minus 1. So let's say that I chose this L as the element to remove and I removed this L. So after removing this L, my score becomes minus 1, right? And I will have some other L dash which could either be 0 or it could be 1. But I would always have this choice to make, right, in the next move. And clearly after even the next move would be odd. So what I can do is I can, in the next move, I can pick this index. And then that would increase my score to plus 1 and the overall net change in my score would be 0. Right. So what I'm saying is, if so basically my net score change would be 0 if I'm allowed to perform two moves. But if my game ended at this move, then that would be a problem, right? So when can my game end at this move? Then my current score is less than equal to 1. So we can say that if my current score is greater than equal to 2, then I can manage to keep my score strictly positive at all the times. Basically, we can make choices based upon this. Right, if 0 0, we can just select any. If 1 0 and odd, then we can select the 1. Even, then we can select the 0. If 0 1 odd, then we can select this one. Even, then we can select this 0. And in case of 1 1, if it is odd, then obviously we will just take this one or this one and our score just increases. So it will remain positive. And if it is even, then we will have to take a minus 1, which on the next move we can get a plus 1, which nullifies this minus 1. So basically, we would have to need our score greater than equal to 2 so that we can take this minus 1, and then on the next move we can again plus 1, so our score does not change at all. So if my current score is greater than equal to 2, then one can manage to keep my score strictly positive at all times. This is the observation. Now, since this was the case in performing the operations, right? We have one separate case as well in the beginning. In the beginning, we don't have two choices, right? In the beginning, we don't have two choices. So we only have one choice, which is k, and it can be either 0 and it can be either 1. So since this is 0 and the move is always odd. So basically we are always adding. So if this is 0, we will add 0 to the score and our score will remain 0. So that is minus 1 case, because, and we can also see this in a test case here. K was given as 1, so we would have to remove this as the first operation, and that would make our score 0, and that is minus 1 case. So basically, this we do not need, and in this case, the score will become 1. So basically, another observation, if S of k is equal to 0, then answer is minus 1. Right? So this, and So obviously now let's imagine that imagine the case where the kth index has 1. So our score will become equal to 1 after the first move. Now what could be the cases after this? So obviously when we remove this element, this would become L and this would become R and our current score will be 1. So obviously we saw that in this case when both L and R are 1, we would have to take this minus 1 if since second move is even, then we have to take this minus one, and that is a problem because if our score is one, then it will become zero, and that would make us lose. So the answer would be minus one in that case. So if on the next step these both are one, then clearly the answer would be simply minus one because when I take this one, my score will become 1, and then again on the second move, I would have to choose from these two ones, and that would make my score 0. So that is not wanted. And then other cases, basically, if both are 0, then I can just pick any one of them, and it's identical. My score will remain at 1 only. And if it is 1, 0, and 1, so again, since the move is even, I can just select this 0, and on the next odd move, I can select this 1. So my score will become after two moves, my score will become 3, basically 2. Because initially my score is 1 after removing this. Then what I can do, I can remove this, so my score remains at 1, and then I can remove this, so my score becomes 2. So in a case like this, my answer is always possible 0 1 0 1 1, because once my score becomes 2, I always have the right choices to make. And in a case like this, basically we can just keep removing the zeros until we get a 1. So again it will match this case only 0 1 1. So we can just remove zeros from any side till we get a 1. So basically identifying from the analysis of all these cases, we can just write the optimal choices that we can make at each step. So what are those? If move is odd, we try to take the plus one if possible, else plus zero. And if move is even, we try to take a zero if possible, else minus one, because then it is inevitable, right? And we can see that these simple greedy choices are matching with our casework pretty good, because here we can see since both are zero, in odd move, first we try to get a plus one, and if not possible, then we just take any zero. One, we take any zero. So and again, if both are one, then in odd we want a plus one, so we can take this. In even, since there are no zeros, it is inevitable, and we will have to take the minus one. Then again, 1 comma 0. In odd, we will take the plus one, and when even, we will take the zero. So that is our greedy choice. And how do we implement this? We can implement this using a simple two-pointer approach. What we can do is we can maintain the two pointers L and R, and once we make a move, we can just do L minus minus or R plus plus. And also one thing we need to remember here is that the array is circular. Array is circular. So the moment L reaches minus 1, it will have to go to L equal to n minus 1. And the moment R reaches n, it will go to R equal to 0. So basically, I am doing this for zero based. since so in zero base r equal to n would be out of indexes, out of bounds, and l equal to -1 would also be out of bounds. So basically we need to maintain a circular array. And how can we see if the elements are taken or not? We will use a visited array for that, this array, to check if the current element is deleted or not, is already deleted or not. So I'll show you guys the code now for this. So basically first I take input nk, then I take the input string s, and then I create a vector n for the string s, which is basically I don't want to deal with these characters later on, so I'll just make them as vector integers, vector of integers. And now I am converting this k to 1 based, and initially my L would be k minus 1 and my R would be k plus 1, and initial score would be v of k. And after the first move, now my move number is second, and this boolean variable check will keep track of whether my answer is possible or not, and the vector level answer would keep the order of the in order in which the indices are used. And this whiz will help us remember that the current indexes are used or not. And we mark whiz of k as 1 in the beginning. Then we run this while loop while true. And I'll explain you guys this while loop. So check is nothing. Check, we just do end of check with score greater than 0. Since obviously if at any point score becomes less than equal to 0, then this check will become false forever. So that's what we want. And these are the two conditions for the cyclicity. Since if L becomes -1 at some point, we can just make L as n minus 1 only if that cell is not visited yet. Because if that cell is already visited, then I can't actually delete that again, so we don't really have this choice anymore. And if r is equal to n, then we just need to see that if not visited 0, then we can set r as 0. And if there are no more elements to remove, that means if L has reached -1 or L is at some position that is already deleted, and similarly R has reached n or R is at some position that is already deleted, then we break the loop. Now this is if the move is even. Yes, if the move is even, so basically we are subtracting the value. So try to subtract a 0, and if not possible, then only then we will subtract a 1. So basically if L is not equal to 1 and L is not visited and L is 0, then we will delete this index and mark it as visited and L minus minus and move plus plus. Similarly, we can check if R is 0, then we can mark R as visited, then push back R in the array vector, answer vector, and then R plus plus and move plus plus. Else, if there was no 0, so now we will have to decrement our score since both are 1, L and R. So basically, we will see that if L is not deleted and L is not equal to -1, so we will visit this L and may push back it our answer L minus minus score minus minus. Similarly, R plus plus score minus minus. In case of odd, since we are adding the values, so again we will check if any of the L and R are not visited and equal to 1. So if any of them are like this, then we would choose that index. Else we will have to go with a 0. So if L or R are 0, then we will just take the 0. So this is, we mark visit L as 1, then we push back it our answer, then L minus minus score plus plus move plus plus. And here what we will do, visit L as 1, answer dot pushback L minus minus, and this time we don't increase score because the value is 0. So this is the two pointer logic, and in the end we again check for the final score is greater than 0 or not. And if the check was become false at some point, then the answer is -1. Else we can just see out this answer array, and since we are doing it in 0 base, we can do I plus 1 for the one based answer. Since every element will be visited at max once only, so all these will be done at max O of n times. So this while loop will run O of n times only. So the time complexity of this solution would be O of n. So that was the problem C. Let's move on to the problem D. So in this problem, scam, you are given an array A of length n where each element is either a positive integer or the value -1. It is guaranteed that A1 is not equal to -1. There are n people numbered from 1 to n. If AI is not equal to -1, the person I votes for the member numbered AI. And if AI is equal to -1, the person I looks at the prefix A1 till AI in the array and considers only the position j is then equal to I with AI AJ not equal to -1. Let frequency v be the number of times the value v appears in this prefix. If there is a unique value v with the maximum freq v, then person I votes for v. Otherwise, if two or more values share the same maximum frequency, person I does not vote. Given a member x, determine whether there exists any valid rearrangement of the known value such that x receives the unique maximum number of votes, that is, x wins without tying anyone else. Note that you may rearrange only the known values arbitrarily among their positions. Positions where AI is equal to -1 must remain -1. Print yes if this is possible and no otherwise. And the constraints we are given, again, the constraint over n is pretty much the same. The difference here is we have AI and x less than equal to 100. So basically, this tells us that the expected time complexity would be O of n log n, right? And what does this tell us? This is basically hinting us towards using some kind of frequency map because these numbers are small, right? So we can create arrays of this size so we can map these numbers. So this is hinting us towards that. So problem D. So basically we are given an array A where if AI is equal to -1, then the vote is not decided, or basically it has some special rules to decide the vote, and AI can be either V or AI can be equal to some V. So this means AI will vote for V. And for AI equal to -1, we will look at J less than equal to I and AJ not equal to -1. And among these voters, if there is a maximum, if there is a maximum, actually, if there is a candidate who got the most votes, then AJ will vote for that. So basically, this is this thing. Let frequency v be the number of times value v appears in this prefix. If there is a unique value v with maximum freq v, then person I votes for v. So basically, if there is a unique value v such that the value of frequency of v is maximum, and is greater than other frequency of other values, so then the person I votes for V. Otherwise, if two or more values share the same maximum frequency, person I does not vote. So basically, there should be a unique candidate with maximum votes. Okay, so let me rephrase this actually. AJ votes for the unique candidate that got the highest, that got the most votes among the voters. AJ less than equal to, sorry, J less than equal to I and AJ not equal to -1. So this is the definition of the problem. So let's see the test cases. So basically we can shuffle these. We can shuffle these. We can shuffle AI equal to V type of indexes, type of indices. So basically the minus ones are fixed. Rest of the numbers we can shuffle with each other, and we need to tell if X can get the maximum vote or not. Basically, can X win without tying anyone else? So if that is actually better. So can X win without tying with anyone else? So we need to answer this. So let's see the test cases now. So the first test case is 4 2 1 2 2 1. 4 2 1 2 2 1. So here there are no minus ones. So obviously rearranging wouldn't really affect the total number of votes. So the total number of votes for one here are two, and for two also there are two. So let's candidate votes. So since one didn't have the maximum number of votes, so the answer for this test case will be no. Sorry, two didn't have the maximum number of votes, so answer is no. Then 2 1 1 2 sorry, my bad. 2 1 2 2. Here we can see that clearly 2 is the maximum here. So the answer is yes. Let's look at this. So 5 1 1 minus 1 2 2 minus 1, right? So let's first try without rearranging anything. So if we don't rearrange, then this will become 1 since 1 is the majority. Then 2 is fixed, 2 is fixed, and then this will not vote because number of ones and number of twos are same before this. So there is not a unique V which has the maximum value of freq V. So that's why this will not vote. So the number of votes again for 1 will be 2 and for 2 will also be 2. So the answer for this is no. And what happens if we try to shuffle this, right? So we have 1 minus 1, 2, 2 minus 1. And we can shuffle these three indices. So let's erase them. And we have 1, 2 and 2 to fill these three indices. So what kind of strategy should we use while filling? So basically these votes are fixed, right? We need to ensure that maximum number of as many voters which have -1, we need to make them vote for X. So we need to ensure that majority of -1s have in the prefix have X as the majority voter. X has the majority number of votes. So what we can do is we can basically start out by filling the array with ones in the beginning, so that now every one will come with the prefix of all the -1s. So that way we can ensure that one will have the most amount of chance to become the maximum for each minus one. So we will put all the ones in the beginning, and since we had only one, so we will put it here, and then the rest two will have to be put here. So actually, this was the most optimal arrangement. And since the answer for this is no, so the final answer will also be no. So let's see the next test case. 1 minus 1, 2 minus 1. And k x is equal to 2. 1 minus 1, 2 minus 1. 1, 2, 3, and 4. 1, 2, 3, and 4. Okay. So let's try without first rearranging the elements. So if we don't rearrange the elements, this will become a 1 and this will not vote. So again the answer for this will be no. Now let's try to rearrange the elements. So we have minus 1 gap minus 1, and we have 1 2 to select from, and x is equal to 2 we are given. So what we will do, as I said, that we will put all the 2's in the beginning. So we will put the 2 and 2 like this, so that now every minus 1 will have all the 2's in the prefix. Maximum number of 2's possible in the prefix. So we put them like this, and then 1 will come here. So after this kind of distribution, this will vote for 2 and this will also vote for 2. So the number of votes for 2 become 1, 2, 3, and 4, and 1 for 1 it only remains 1. So answer is yes. So what the observation we can write it down. After rearranging, we will put all the x in the beginning, so that every minus 1 will have the maximum possible number of x in its prefix. And that way we can ensure that the chance of x being the maximum frequency element is the highest. Now let's move on to the next test case. So 1 1 2 2 minus 1 1 minus 1. So 1 1 2 2 minus 1 1 minus 1, and that is x is equal to 1. X is equal to 1. So we need to shuffle these, right? Minus 1, and we have 1 1 1 2 2. So obviously we will put the ones in the beginning, as we discussed, 1 1 1. Then we will have to put the 2. So after this distribution, we can see that this will become 1 in the final array, and this will also become 1 in the final array. So clearly 1 is the majority here. So the answer is yes. And then 1 minus 1, 2 minus 1, 2. 1 minus 1, 2 minus 1, 2, and x is equal to 1. So this is in fact the most optimal arrangement, since all the ones are in the beginning. So after this minus 1 will become 1. This minus 1 will become also 1. So the number of voters for 1 would be 3, and the number of voters for 2 it will be 2. So the answer for what? 1 minus 1, 2 minus 1, 2. 1 minus 1, 2 minus 1, 2. Oh, okay. One very important point I have forgotten, that we only consider only the positions j less than equal to I with aj not equal to minus 1. So actually for this minus 1 we will only look at these two indexes, and since 1 and 2 are tied here, so this minus 1 will not vote for anyone. So the number of votes would look like, for 1 there are 2 votes, And for 2 also there are 2 votes. So the answer for this test case is no. So basically we have decided that what to do with the x we have decided after the rearrangement, what to do with the x we have decided that. But in the test cases we had only two numbers. We had only 1 and 2. So basically, we were just placing one in the x's in the beginning, and then we can just place the other left numbers. But there can be multiple different numbers, right? So what do we do after we are finished placing x? So let's take some example. Let's take this as the example. Yeah. And we have, let's do this. Okay, and we have 1, 1. Then 2, 3, 4, 5, and 2. Okay. So 1, 1, 2, 3, 4, 5, and okay. 2, 2, 3, 4, 5. Let's say that we were given this problem. These two are -1, and we are given these voters to distribute it. So 1, 1 will come in the beginning. We are taking x as 1. So these two are done. So we have these many left. So what can we do? Let's place 2 here. Then obviously we will try not to place in any of these places, right? Because what that will do is the number of voters for one and number of voters for two will then become same, and then this will not vote. So we can follow this strategy. We can maximize the distance between the same elements. What this will do is basically after 2, we will avoid placing the other 2. We can go to 3. And after 3, we can go to 4. And after 4, we can go to 5. Now, after placing 2, 3, 4, 5, we don't have any other choice, right? Because we only had numbers 1, 2, 3, 4, 5. And now the next number, whatever we place, would already have been placed before. So the only choice we have is to now place 2. So that way, because of arrangement like this, the distance between these two tools have been maximized, right? You can see that it has been maximized. We tried to place as many distinct elements as possible. So this strategy can be used so that the tools are maximized, distance between tools are maximized so that the chance for these ones to be the maximum would be the highest that is possible. So we can use these two strategies to generate the best possible array and then count the number of votes. Let me explain the second observation a little better. So let's say that we need to arrange, let's say that x was equal to 1, and so we had placed all the x in the starting, and then we need to arrange these elements 2, 2, 2, 3, 3, 3, 4, 4, 5. So how we will arrange these elements? We will arrange them like this. We will first take a 2, then we'll take a 3, then we'll take a 4, then we'll take a 5. And now since we don't have any other choice, we will have to repeat an element. But again, after this 2, we try to place this 2 as far as possible, because the moment we place this 2, the number of voters for 2 becomes 3. So that we don't want. So what we can do is place 3 after this 2. So still, since there are 2 voters for 2, there are 2 voters for 3. That does not increase the maximum number of voters, since it is already 2 here. And then next we will place 4. And now, since it is immutable and we have to place this 2, so we will place it and then we will place 3. So we can follow this type of strategy to create the most optimal, and then we can just simply count the number of votes for x and see if that are greater than from the others. So this can be implemented on O of n. I'll show you guys the O of n to 100 actually. I'll show you guys the code. So basically I take input vector v, and in this array f, basically I'm storing the number of votes for the candidate. Basically, f of I stores the number of votes for I. F of I stores the number of votes for I. Fixed votes for I. So if V of I equal to minus 1 continue and f of Vi plus plus. So basically I'm storing the total number of votes for each candidate, and then this for loop will decide the optimal arrangement. So basically I'll explain what this variable C does. For now, since we are literally just continuing when V of I is minus 1, because V of I equal to minus 1 are fixed, right? Else, what we are doing is basically, if we can place an x, that means if the frequency of x is positive, then we would just place x at v of I and decrease the frequency of x. And the moment we use up all our x, then we won't be entering in this if condition, then we will enter in this else condition. So that is after we are done placing the ones, and now it's turn to place these numbers. So what we will do is, I'm maintaining this C variable, which basically denotes the, so initially C is equal to 1, then C is equal to 2, then C will become 3, then C will become 4, then C will become 5, and then again C will become 2. So basically C is keeping track of the elements. After 4, C will become 3. So how is this happening? Basically, initially we set C as 1, and in this else loop, we just keep on increasing C while the f of C are 0 until we reach a certain C which has some positive frequency. And again, if C reaches 101, then that means we have reached the end. So we will reset it at C equal to 1. And once we get some candidate which has FC greater than 0, so then we will just put that value at V of I, and then FC minus minus, and then C plus plus. And now to calculate the final vote counts. So FVC is the final vote count, and VC is the prefix. This is the number of fixed vote counts in the prefix. So basically, in this for loop, first of all, if it is a fixed vote, then we can just do VC of V of I plus plus and FVC of V of I plus plus. FVC, F is nothing but fixed vote count. F is nothing but final vote count actually. Since in this we need to not count the AJ which are minus 1, right? We don't need to count the votes where AJ are minus 1. So that is why I have created two variables, one where I will store the count of these also, and one where it will count without these. So now let's decide for the VFI. So for VFI, we can just see if any of the candidates in 1 to 100 have the maximum frequency or not. So we can maintain two variable, val and candy. Candy denotes the candidate and val denotes its frequency value. So if VC of J is equal to val, that means that some other element has a frequency equal to our frequency. So that means our candidate was not good. And if the VC of J is greater than val, that means the frequency, we have found a higher frequency. So we will update our candidate and update our value. And in the end, if we have found some possible candidate, so then we will update the final vote count for that candidate. And then we can see that if the final vote count of X is greater than for all other candidates, then the answer is yes, else the answer is no. So that is the solution for problem B. So I am done with the discussion. Thank you.